Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 24th, 2026, about 6 days ago. It proposes a unified stochastic formulation that bridges Monte Carlo rendering and diffusion-based generative modeling, allowing for physically grounded control over things like shading and material properties. The paper is titled, Bridging Physically Based Rendering and Diffusion Models with Stochastic Differential Equation. And as we'll see later, the results for material editing are really impressive. So to visualize this connection, Figure 1 places the two paradigms side by side. The top row demonstrates Monte Carlo path tracing, where the process begins with a grainy, noisy estimate and gradually converges to a clean image as more light samples are computed. In parallel, the bottom row shows a diffusion model starting from random noise and refining it step by step into the same visual result. This shared evolution from noise to clarity is the key observation that allows the authors to link physical rendering directly to generative modeling. Now, Figure 2 formalizes this intuition into a rigorous mathematical framework. The top blue panel represents the path tracing process as a stochastic differential equation, which the authors call the MCSDE. Here, the rendering converges from high variance to a clean image as the variable tau, representing variance time, approaches zero. The middle gray arrow establishes the connection, showing that this rendering process mathematically mirrors the reverse dynamics of a diffusion model. Finally, the bottom yellow panel illustrates the resulting diffusion SDE, where the model uses this aligned timeline to denoise the image, effectively allowing physical rendering parameters to guide the generative process. So, with that framework in place, Figure 3 demonstrates the practical effect on material appearance. Here, we see a reference rubber duck edited into two distinct materials, a highly specular metallic version on the left and a matte, diffuse version on the right. The authors achieve this by exploiting the fact that specular reflections have higher variance and stabilize later in the diffusion process. The histograms below confirm the difference. The orange curve for the metallic duck is sharp and heavy-tailed, capturing those intense highlights, while the green curve for the diffuse duck is much smoother and compressed. So Figure 4 puts this theory into practice by demonstrating how the diffusion model takes over noisy, path-traced images. The top row displays the inputs, which are grainy renders with extremely low sample counts, ranging from just 1 to 7 samples per pixel. In the second row, a standard baseline attempts to denoise these but essentially fails, producing undefined, glowing blobs because it misinterprets the specific statistics of Monte Carlo noise. By contrast, the third row uses the author's proposed tau mapper to correctly align the noise levels, which successfully recovers the distinct 3D shape of the dragon. Finally, the bottom row introduces a lightweight adapter to fix the color distribution, resulting in a clean, high-fidelity output that closely matches the ground truth. Well, while the previous figure focused on reconstruction, Figure 5 demonstrates fine-grained material tuning. The top row illustrates increasing roughness on a bunny model, moving from a sharp, glossy reflection on the left to a dull, matte surface on the right. Below that, the second row increases the metallic parameter on a birdhouse. You can see it transform from a matte, wood-like texture into a highly reflective metal surface, showing that the model successfully maps physical rendering parameters into the diffusion generation process. Now, Table 1 provides the quantitative metrics for this diffusion-based denoising. The second row reveals that the standard baseline performs poorly, achieving a peak signal-to-noise ratio of only about 11. In contrast, using the tau mapper alone, shown in the third row, boosts this score to over 19. Finally, the bottom row demonstrates that adding the adapter yields the best overall performance, effectively tripling the structural similarity score compared to the baseline. Wrapping up, this research proves that unifying rendering and diffusion under one stochastic framework offers huge benefits. It enables diffusion models to act as super-efficient denoisers for 3D engines, while giving artists physically grounded control over material properties. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.